Welcome to qnawire.
All right, so what we have here is a biophysics question. There's this type of insect, and insects are cool because they can exert forces that are many, many times greater than their body weight, and we'll be exploring that in this problem. So just to start recording some information that's given to us, we know that the insect is 12.3 milligrams. However, let's just go ahead and convert that to kilograms right off the bat because we know that we want our units to be in SI for the units to work out so that we get final answers of newtons in terms of force. The frog exerts the forces on itself against the ground and ends up at a takeoff speed of 4.0 meters per second. And then we know that the duration of the exertion of its muscles was a delta t of 1 millisecond. But again, I'm going to convert that to SI units, or seconds, in order to get us started on this problem. So that's the information that is given to us. We can go ahead and jump straight into part A, where we need to draw a free body diagram for the frog. So ultimately, it's going to be the normal force, or the Newton's third law force of the ground pushing up against the frog that's going to be propelling it. So I need to draw that as being a lot longer than the force of its weight. So that's why one arrow is so small and the other arrow is so big, because the frog is jumping, it needs to be going upward. And then in part B, we are calculating exactly how hard the frog needs to accelerate itself in order to attain that height. So we know nothing about the position, but we do know things about the velocity and the time. So let's use the average acceleration formula in order to find that. Delta v over delta t, or delta v is the final velocity minus the initial velocity, and then we'll just leave the delta t as delta t because we know the duration. One thing that I did not mention before was that the frog begins at rest. It's just sitting on the ground, so its initial velocity was 0, so we can go ahead and cross that out. So we just get VF over delta t. So we can go ahead and plug in those numbers of 4 on the top and then 10 to the minus 3 on the bottom, so that at the end of the day we get an acceleration of 4 times 10 to the positive 3 meters per square second, or 4,000 meters per square second is the very intense acceleration that the frog needs to apply on itself. And sorry, that was not the answer. That was the first part of the answer. Now that we know the acceleration, they want to know what the magnitude of the normal force was specifically, or how hard the frog pressed up against the ground. So moving forward with that, we now apply Newton's second law. So we need to know what the net force is. So we tally up all the forces. That's going to be normal force minus the weight force. So that's mg. And then Newton's second law tells us that this is also equal to the mass times the acceleration that we just found. So again, we're interested in finding the normal force. So let's go ahead and isolate that by adding mg to both sides of the equation. And then I'll just skip a little step by also grouping some terms together, factor the masses together, so that we can go ahead and start plugging in numbers. Remember, the mass was 12. Sorry. What is going on? 12.3. There we go. Times 10 to the negative 6 we saw, and then we're going to add the acceleration to the acceleration due to gravity. So this one, I'll just write it out, is 4,000 plus 9.81 is the acceleration due to gravity. So we plug those numbers in and get that the force, which is going to be kind of underwhelming, 0.0493 to 3 significant figures, newtons. It is a small force, but remember this is a small bug, we're measuring it in units of milligrams. So quite underwhelming, but we can put this into perspective by trying to figure out what the ratio of its normal force to its weight is. So in other words, how strong can it push itself compared to its own weight. So let's find that ratio. That's going to be the normal force that we just found divided by mg. Plug in some numbers. The number that we just found, 0.0493. On the bottom goes the mass. multiplied by the acceleration due to gravity. I don't know why I made that so big. And then the ratio of the normal force to its weight is approximately 409. That's very strong.